All right, good morning, everyone. My name is Jack Panopoulos. I'm an application scientist for FlowJo at Vidi, and today we're going to be going over my AAI talk that I gave just over a week ago. So let me just put this in presentation mode so you guys can see the full screen. And then I'm going to try and choose a little laser pointer here so that you guys can see things as I point them out. All right, so in case you're wondering, Vidi, vici, idolum, kind of a play on words of Vidi, vici, right? The Julius Caesar, I came, I saw, I conquered. This translates to I came, I saw, I tracked. And we'll be kind of talking about a high dimensional workflow in today's session. So when I was back in my grad school days, and when I was a postdoc, most of my work was done with 4-color, maybe 6-color assays, and all of my results, for the most part, I could compare them just by setting up a series of 2x2 plots, looking at the frequencies or the shifts in the MFIs of, 1 or 2 populations that I was looking at per experiment, and then coming up with some sort of conclusion. But the advent of multicolor flow cytometry, really spectral cytometry, new reagents, of course, that allow us to put colors into a much larger portion of the spectrum, and even the software tools that kind of have come along with these advances have all kind of made the analysis of flow cytometry data more complex. And once you start to get, I would say, above 10 colors or so, the number of dimensions that you're going to be looking at, if you had to go by 2x2 plots, starts to become unwieldy. And you will invoke a lot of these tools here that will, require, if you were to do it in a 2x2 sense, you come up with a lot of mind-blowing combinations. So for example, if you have a 12-color panel, you could have, 144 different 2x2 color combinations. And if we get upwards of 40 colors, which has been published, we're talking about 1,600 color combinations. So we invoke these tools like t-SNE or UMAP, some of the clustering algorithms, to help us to digest these data and to make sense of them. Once we invoke these tools, however, we may find cells of interest, that are popping up, that are driving, let's say, they're driving the hypothesis, or they're driving the phenotype that we are observing. And then it becomes a problem of, okay, well, I've identified these cells, but how do I now sort these cells, especially if they've been algorithmically determined, right? If I used a clustering tool, or if I gated on a t-SNE and I'm trying to figure out how to sort a particular population that's been gated on t-SNE, how do I translate that back to a series of manual gates? So you'll probably, if any of you have done this, you probably have experienced the problem of, figuring out the best series of 2x2 gates to get you to the back to the cell sorter to isolate those populations. Okay, so in order to approach these types of problems, I think it's very important to have a map as to how to approach these, right? So you know which steps come first, and then which steps come next, etc., so that you have a general workflow to have with you while you're on this journey, so to speak. I apologize, I'm overcoming a cold, and so I'm a little bit under the weather. But the first step in the high dimensional workflow, and it's common with, of course, our standard immunophenotyping, let's say, of a low parameter or low dimension workflow, and that is data quality control. I'll talk about the specifics there momentarily. But it's always important to make sure that the data are in good quality before you pass them into t-SNE or UMAP or any of these clustering algorithms. And the primary reason for that is, dead cells, debris, doublets, those types of things can really strongly impact the results that you get in the end. And in fact, dead cells are very nice looking populations of cells. They're bright for everything, and before you know it, you're going to have a population that you discovered that you can't actually manipulate, or I'm sorry, you can't actually reproduce. I apologize, there was a chat message in the chat screen there that they can't hear me, but I think my microphone is on and their audio may not be connected. I hope the rest of you can hear me. So after data quality control, you may want to employ a normalization step. This is particularly useful for longitudinal studies where you're gathering data, let's say on day 1, and then you have another set of data that are going to come in on day 30, and then 6 months down the line, and then maybe a year down the line. You want to be able to amalgamate those data so that everything is pretty much on the same scale. Also, if you're collecting data over multiple sites that are spread geographically, so for example, you may have a cytometer in Los Angeles, another one in New York, another one in London, right, and who knows where else around the world, and you want to make comparisons between the samples or the patients that you collect in all of these different locations. And so normalization is useful for amalgamating such data. The annotation step is also very important. I'll dig into this a bit. It's probably the most unglorious step in our analysis workflow here, but annotation is absolutely crucial, especially if you're doing high dimensional workflows, because what you want to do in the end is you want to cross compare all of your experimental variables, right? So envision that you have an experiment where you've got multiple patients that have, let's say, been you've acquired their blood, for example, on pre-treatment, post-treatment after, let's say, 7 days, and then post-treatment after 30 days. You want to be able to not only compare those time points, but you might also have different age cohorts. You might have different ethnic backgrounds. You might want to separate the sexes and compare them. Does this disease affect men more than women, or vice versa? And if you're collecting, of course, different tissues, that's another experimental variable that you will want to cross compare, and you want to do that as fast as possible. And the only way to do that is to properly annotate the data. So we'll talk about that as well in a little bit more detail. I should probably put a star around the concatenation step, because the concatenation step is the primary bifurcation point. This is the step that makes analysis with these tools, the high dimensional tools, different than your standard immunophenotyping experiments where you set up your gates, you look at this population, the MFI, and then you compare that to tube number 2, same population, and whatever their MFI happens to be. The concatenation step, what we do here is we merge all of the files that we want to compare. We merge them all into a single file first. So imagine your entire cohort, whatever it is that you wish to compare, you need to put it all together into one file first. Then you can do all the downstream steps. So the concatenation step, again, it's unglorious, but it's an extremely necessary and crucial step for all of the downstream stuff that we're going to take a look at. Okay, so after the concatenation is done, we can do some dimension reduction. So this usually refers to tools like t-SNE or UMAP. You may have heard of TriMap. There's a new one out called PackMap. another one called embed sum. There's a number of these tools out in the environment, and I'll talk about which ones you'll have available to you in FlowJo to use. But dimension reduction is extremely useful for making comparisons, and we'll see that momentarily. Clustering. Clustering and dimension reduction usually go hand in hand. I find that, each is useful on its own, but only to a limited extent. I like to use these two sets of tools in combination with one another. So oftentimes, even though I have them separated here, I generally will recommend to people that you use both of these together. Clustering tools are extremely useful for processing large amounts of data very quickly. They also provide a fresh perspective on the data, so we'll take a look at that as well. And then after you're done with your dimension reduction and clustering, you will usually do a phenotyping step, which is characterizing the clusters or characterizing the little lobes that you see in a t-SNE or a UMAP plot, figuring out what those different islands happen to be phenotypically. And then after that, you may do some sort of comparison. Now, the order here may be switched. You could maybe do some comparison first and then do the phenotyping. It's really up to you. But the comparison step to me is the all-important one, because this is where we finally get the results that we're looking for to figure out what is different in the system. The latter steps that I have written here, we'll talk about tracking. And then we will also talk about how to isolate those cells that you find so interesting. So let's see here. I need to advance to the next slide. And apparently I have to do that using the little arrow down at the bottom. All of the tools that I'm going to be talking about today, these are freely available on our Exchange site, which is just exchange.flowjo.com, or they are built into the FlowJo software itself. So for example, t-SNE is already there. And there are obviously the concatenation platform is already built into FlowJo as well. Okay, so let's talk about data quality control, because this is again, it's very important, but sometimes I feel like people don't spend enough time reviewing it. The example that I put in front of you here is we have a flow cytometry file that has a clog in it. In the first few seconds of acquisition, you can kind of see these striated lines. You can see data points here that are shifted downward relative to the rest of the acquisition. You also have some data points up here that are shifted upward. So you can see that the data points that are taken in and around a clog are not exactly what you want to filter down into your analysis, right? These guys up here are gonna look like false positives of some kind. God forbid, they're a rare, turn up to be like a rare population or MRD, and then likewise, the opposite would happen with respect to a false negative, perhaps. So what we wanna do is A, we wanna be aware of this, and B, we wanna be able to take this out. Now you can do this manually if you want, and it's estimated that about 10% of flow cytometry data files, those that are located in the public repositories, about 10% of them have clogs or other anomalies associated with them. So if you figure, 10% is pretty big number, it's worth looking at your data to make sure that this stuff is not filtering into the results. Okay, so either create a manual gate or make use of either one of these tools, FlowAI or FlowClean. Again, these two are plugins, and they're automated tools that will automatically go through and chop out the clog in this case for this data file. And what it will leave you with is a population labeled bad events and another one that is labeled good events. And of course, you would put your gating hierarchy underneath the good events branch. Okay. My personal favorite is FlowAI, simply because it's faster and it has a few more checks than FlowClean does. So to give you an idea of the speed, if you have 50,000 cells per well in a full 96 well plate, and you're talking about, 12 dimensions, It'll take FlowAI about 5 minutes to churn through the entire 96 samples and create good events and bad events, whereas FlowClean will take about, I don't know, about half an hour to do the same job. So if you have the time, I guess FlowClean is equivalent, but I would, I personally like FlowAI. All right, so data quality control continued here. I think it's worth mentioning compensation in the data quality control section because to date, we give probably one seminar about compensation every 3 months, and it's always well attended. And I think because it's probably the most important factor affecting proper interpretation of cytometric data, and yet it's the least understood, I think, of all of the problems that can happen with your data. But to help you with this, FlowJo has several different ways to compensate your data. So you may do it on the machine, right? You may set up your compensation on the machine, and whether you have a spectral machine or you have a standard, traditional cytometer doesn't make any difference. FlowJo has the ability to do spectral deconvolution or spectral unmixing, and we have the ability to optimize the weights. So generally speaking, the spectral algorithm is a linear least squares algorithm, and you have the option to weight various fluorochromes if you want, or you can weight them all or let it occur automatically to best deconvolute the data. There's also another algorithm that we've implemented in FlowJo, and it's been there for a while now. I want to say at least 2 years, but this mechanism is called autospill. This is another way to compensate your data that I'm very bullish on, and the reason is the setup for compensating the data. Really, all you need is a gate that has some positive cells in it or beads, and you don't need a negative. So what this method does, it's a linear regression curve that it sets up, and it basically just looks at the spread in the data and tries to zero out everything across all the different colors that you have. Very easy to set up, very fast, and I have to say that the time savings alone, the fact that the results are very comparable to your traditional method, I think is definitely worth giving it a shot. So in addition to getting your compensation, again, your compensation has to be top-notch when you're using these high-dimensional tools, because if you have one sample that has been overcompensated or undercompensated with respect to a given population, guess what happens when you run dimension reduction or clustering, right? Those overcompensated populations or undercompensated populations, whatever it may be, are going to appear to be new unique populations to either the TISNE, the UMAP, or the clustering algorithm. So again, it's very important, and we have the tools here to help you, sharpen that. You can also compare your compensation matrices to one another. So I know it sounds rather onerous to say, hey, try out all these different, methods of compensating your data, but the cool thing is that you can compare the data, or you can compare the compensation matrices that you generate using these different methodologies very quickly in the matrix editor by just simply highlighting the two compensation matrices that you wish to compare. And in this case here, you can kind of see how the blue cells are separating away from the red cells along a certain set of parameters. In addition to that, we calculate, if you run your compensation in FlowJo, you can calculate the spillover spreading matrix or the total spread matrix, and the output here will help you with your panel design. So obviously what will happen is you'll get a grid that looks something like this. You'll have some cells that have a very dark red indication. Usually the dark red boxes are going to be the colors that have a lot of interference. So you probably want to reserve this color combination for two mutually exclusive markers like CD3 and CD19 or something like that. Okay. so let's move to the next slide here. Normalization, as I mentioned, the way we achieve this is by a plugin called CytoNorm. We just gave a webinar on this, I think, last month, maybe the month prior. I can show you later if you guys are interested where we store our recorded webinars. So everything that we've done, we record all of these webinars, and you can always review them later. But the CytoNorm package, pretty straightforward. You pick out your samples, you go ahead and assign reference controls to them, and then in the end, what will happen is the algorithm will go ahead and normalize those data files, and then it essentially re-exports normalized data. So you'll run the plugin, and then you'll get a new set of data files, FCS files that have been normalized. Okay, the annotation. Again, I mentioned this in the beginning, extremely important for making our cross comparisons. How do you do this in FlowJo? There's a couple of different ways. There's a keywords band located underneath a workspace tab. There are several tools within that band to kind of help you with a one-off situation. So if you just want to label something with the same value, copy value to group is pretty handy. Create value series is extremely useful if you want to set up a pattern with your files and the associated keyword. But my favorite option here is the plate editor. And the plate editor is this tool that allows you to import a CSV worth of data into and tag that, that data or that metadata along your FCS files. So for example, here, the structure of the file looks something like this. You have to have a well ID declared in the first column. Then, of course, you have to have all the well ID assignments, but then whatever other column you want to add, the column header can be whatever it is. Here, I've just marked doxycycline, cohort, age and sex, any transgene, et cetera, that was associated with it. All of this information can be brought in a few clicks using the plate editor. Okay, and then once you create these annotations, what ends up happening after we do the concatenation step is that we convert all of these different column headers essentially into gateable parameters. So this is what it will look like in the concatenated file, and you can actually gate, oh, here's my 0, or my vehicle treated cells, and then I have my doxycycline that have, 1 microgram per mil or whatever, and then so on and so forth as you move up your dilutions. But you can gate on them, and then of course you can overlay them and see if there's any difference when you get to the end. So again, annotation, I can't underscore this enough. Use the plate editor to bring in a bunch of data. If you only want to, bring in a little bit, you can go ahead and use the keyword band to do one-off type of annotations. Okay, the concatenation step. This exists underneath the document band, and usually this is located underneath the FlowJo tab. So the very default tab. When you open up FlowJo, this is where it's going to appear. The export concatenation button is located within it, and it'll pop up a menu that looks like this. It is in this menu that we add the additional parameters here. This is where you add your keywords that you imported using the plate editor or the keywords band. You will go ahead and add those keywords in this particular location. Then when you concatenate the files, you'll get, again, this kind of a setup where you can gate on the different concentrations of, in this case, doxycycline or whatever else you had, in the data set. Now, concatenation, not only useful for high dimensional work, but if you're doing titration experiments, it's very easy once you concatenate your files to identify which sample has the best stain index and therefore will be the optimal concentration to be using in your particular experiment. So it's extremely useful platform. I feel it's a little underutilized, but you need it. You absolutely need it if you're going to do any of the high dimensional work. Okay, so as far as dimension reduction, now we can start to get into the fun stuff. Dimension reduction. there are several different tools that are available to you in Tisney or in in FlowJo. So there's Tisney, there's UMap, there's TriMap, and the new one that I mentioned earlier, PacMap. All of the stuff that has sort of the suffix map here, right? PacMap, TriMap, UMap. These three guys, for the most part, they're said to have better global structure of the data, or representation, better global representation of the data. And what that means is essentially that cells that are more highly related to one another are juxtaposed to one another closer in two-dimensional space here than cells that are more divergent. So for example, if we look at the CD4 T cells, which are in red in all of these plots, versus, for example, the NK cell population, you can see that CD4s and NKs in the UMAP plot are pretty far apart from one another, right? Same thing in the TriMap plot. You can see that the islands are pretty far away. The PacMap, same story. But when you go to Tisney, you'll notice that, you know, the CD4s are all throughout the middle here. And then, you know, on either the right or the left side, you can quickly see that there are these green NK islands very close juxtaposed to the CD4s. Okay, so Tisney doesn't do such a great job with a global structure, whereas the UMAP, the TriMap, any of the maps tend to do a better job. Okay, in contrast, cells that are more highly related to one another are a bit closer in time or in space here. So for example, the CD19s and your monocytic cells, you know, tend to juxtapose a little bit closer together in space than they do, say, with the T cell fractions. Right, same thing over here and same thing over here. Monocytes and B cells are very close. In the Tisney world, they're, in this case, you know, the monocytes are kind of all over the place, and they're very, you know, they're juxtaposed very close to all other types of cells. So again, not doing such a great job with respect to the global structure. Okay, my personal opinion, like, it kind of depends on what your analysis you're trying to do. If you're doing trajectory analysis, right, or you're trying to understand how does one cell type start expressing antigen, and in what direction do they migrate, right? Do they become more, let's say, monocytic, or do the monocytes become more NK-like or more B cell-like, whatever? The map types of projections are kind of useful, because what you can see here in the UMAP, for example, is you have these two little peninsular populations. This is an indication that, okay, whatever these cells are, they're still monocytic, but they're probably beginning to express a single marker that is different from the bulk of the population that is present here. So it's pretty intuitive when you're looking at this that you have, okay, these are probably cytokine expressors that are starting to change in the system. And that too is reflected whether you're looking at PacMap or TriMap. Whereas in the Tisney, you don't see that quite as intuitively. However, what I will say in Tisney's case is that Tisney tends to break up the populations a bit better, in my opinion, than the UMAPs, the TriMaps, or the PacMaps. And so very fine-grained differences, phenotypic differences between the primary population of monocytes, right, which probably is going to, you know, again, correspond to this large island right here. You can see that it gets broken apart into multiple smaller, tiny islands. And so sort of the nitty-gritty details are reflected by the separation of all the different islands. So it kind of depends. I like to use Tisney when I'm comparing two different conditions and I'm just looking for different phenotypes that are present. But if I'm going to do some sort of trajectory analysis, or where I know that my cells are going to start expressing cytokine of some kind and going to be moving in some particular direction, I might opt to use the TriMaps or the UMaps, whatever the map functions are for that type of analysis. So really, again, it's kind of a matter of taste and, you know, how you like to visualize your compressed results, if you will. One of the other things you can do with the, you know, with all of these dimension reduction techniques is rather than doing what I did in the previous slide, which was just taking manual gates and overlaying them onto the t-SNE or the UMAP plots, what you can do is you can also just generate a heat map to kind of orient yourself and to figure out, you know, where the, in this case again, where the monocytic populations are, you know, which ones are expressing cytokine. For example, these monocytes here in the upper left are my activated monocytic cells expressing both IL-1, maybe to some degree they're expressing IL-6, and of course there's some TNF there as well. My plasmacytoid dendritic cells locating themselves in a different island altogether, and pretty quiet with respect to antigen, other antigen expression or cytokine. Okay, so clustering, as I mentioned, is a quick way to cut up the data. So if you have a lot of backlog data and you want to process it very quickly, clustering algorithms can be quite useful because they're much faster at cutting up the data than humans are. There are several different clustering algorithms available to you in FlowJo. This is just one of them. It's called FlowSum. I'll show you some others here momentarily. But the other thing that I always recommend people do when you're using the clustering tools, maybe you're not going to use it to gate your data, because ultimately, you know, we want we want to put our hands on the data and make sure that the clustering algorithm is actually identifying the proper set of cells. But one thing I will give credit to the algorithms for doing, and this is what I will recommend why you should use these tools, is that the clustering algorithm has the unique ability to pull out populations of cells that we may not be privy to. And the perfect example of this, I think, is cells that have mid-expression for a given marker. It doesn't have to be a cell surface marker. It could be cytokine, right? Oftentimes when we set up our 2x2 gates, we're gating everything exclusively as plus minus, you know, this is in, that's out, etc. But the algorithm has this, you know, ability to visualize the data essentially in all dimensions, all at the same time. And so a lot of these mid-expressing populations are distinct, not in the mid-expression of the cytokine, but perhaps along some other cell surface marker. So you'll get populations of cells that, again, if you're doing trajectory analysis, these are going to be the ones that are sort of migrating from one location to the next. And so I think that clustering algorithms can kind of give you a fresh perspective on the data that you wouldn't otherwise see if it weren't for the algorithm. Okay, so in addition to FlowSum, which has a visual output, as you saw there, the minimum spanning tree. I'll talk more about that in a moment. But there are other algorithms called phenograph, XShift. There's another one, FlowMeans, that I didn't mention. FlowMeans is one of the very first algorithms adapted for flow data. But all of these tools are available as plugins in FlowJo. You just put the plugin jar file there and you basically click run. And what will happen is it will spit out populations for you in the workspace. So for example, here we can see that when XShift is done running, it just says XShift and then population 21, right? And then XShift, population 20, blah, 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 all the way on down. The problem with the clustering algorithm is that it doesn't tell you what the phenotype of the cluster is. So that's why you use it in conjunction with your UMAP or your t-SNE plots, so that you get an idea of what the phenotypes of each of these clusters happen to be. And then you can also infer, what is it that the clustering algorithm sees in terms of populations versus, let's say, UMAP. So if this is the monocytic population and kind of this light green color down here, you can see that for the most part, XShift thinks that, this is one entire population rather than 2 or 3 as UMAP sees it. This island, of course, or this little peninsula being a different population according to XShift. Okay? And same thing with some of the populations over here. Okay? Phenograph, on the other hand, has also a different opinion. So, the way the mathematics works in each of these clustering algorithms is going to be different. and therefore how they interpret the populations is going to be different. So you will see that, in this case here, phenograph thinks that this big island over here is one solid population, whereas XShift is breaking this up into 2, possibly 3 populations. Okay, so obviously it's going to be up to us to figure out, okay, what the heck is the algorithm doing and why does it see that these populations are different? Okay, and so for that, in order to figure that out, to make comparisons between the clustering algorithms, you can use another tool called the Cluster Explorer. Cluster Explorer can only be invoked after you have run a dimension reduction of some kind, so t-SNE or UMAP, and a clustering algorithm of some sort, so either FlowSum, phenograph, XShift, or FlowMeans. But then once you do that, you'll get a series of panels. My favorite, or at least one of my favorites, is this line trace plot. So this plot will put all of the different clusters that you have in a given run. It will display them as different colored lines. And then the y-axis will be the relative expression of any of the given markers here. So the markers are going to be listed on the x-axis, and their relative expression is on the y. So you can see here at the top, okay, these clusters or these populations of cells, these are CD16 positive, your non-classical monocytes, right? So on and so forth as you would go on down the list. Now, the super cool thing about this particular panel is that you can gate on it. So you can filter your results. In this case here, I've created a gate on cells that are CD56 positive, my NK cells, also those that are expressing CD3, but then I have excluded any of them that are expressing, I believe it's CD14 here. So there's Boolean logic that you can incorporate into these gates, and you can filter the list down so that you can kind of study one cluster at a time, or let's say a particular phenotype at a time, and see how many clusters you're generating per population. All right, my favorite tool though, within the Cluster Explorer, and I'll explain this a little bit more, is this heat map table. I don't particularly like the heat map table for phenotyping. This to me makes me dizzy. But this table has another powerful function that I will get to in a moment, and that I believe makes it the ultimate tool in the toolbox here when you're making comparisons between conditions. Okay, but there are several other panels. For example, there are a bunch of 2D plots that you can make, and that will allow you to backgate any of the populations that you see onto your UMAP, or you can look at any 2x2 set of expression. These axes are changeable. Okay, so for comparison purposes, there's a couple of ways that you can approach comparing the data once you have done dimension reduction and clustering in FlowJo. The first and probably the easiest method is to simply overlay the two conditions, or however many conditions you have, on top of one another in the layout editor. So again, if you have annotated the data, and let's say you have a cohort that's wild type, and then you have another cohort that is your knockout, you can simply create a gate on the knockouts and a gate on the wild type, and then you just overlay those two gates. And then you display it or project it in the two-dimensional space of t-SNE or UMAP, and this is essentially what you might see. So in this example here, I have two sets of files. I have files that have been stimulated with a toll-like receptor agonist, and then I, of course, have cells or files that have not been stimulated, and I simply gated on the two conditions after I labeled the files, and then overlaid those gates in the layout editor here, and you're just looking at the two different conditions in UMAP or t-SNE space. So here you can see that the non-stimulated cells occupy what appears to be the northern half of this map, right? And then the stimulated portion, a bunch of other cells on the sort of the southern half. And as you can kind of infer just by looking at the graph again, there's more islands in the stimulated subset than there are in the non-stim, which is kind of expected when we dump some sort of agonist on our cells, we expect them to become angry. And if you have a heterogeneous population to begin with, we expect that all of those different populations are going to react differently, expressing different subsets of cytokines, and therefore you're going to get multiple islands in the stimulated instance. Okay, you can further break this down if you don't want to look at just the entire, subset with one another. You can break this down by compartment. So if you have a gate set up already that identifies your monocytic populations, you can see here, okay, the vast majority of resting state cells here were antigen presenting cells or CD14 monocytics cells. When we actually stimulate, the monocytes change, they form this island over here and a series of other smaller islands just to the south of this guy. Okay. Same thing if you had, in my case here, dendritic cell gate, gating on CD1C. You can see that in a non-stimulated state, they occupy a particular location, and then when you stimulate them, they they enhance, probably in frequency. I didn't, put the frequency gate here, but I'm just inferring that there are many more cells once you've dumped the stimulus on it than you had when you didn't stimulate. Okay, in the case of the plasmacytoid dendritic cells, very few cells exist in a non-stimulated state. Once you dump the agonist on there, you get more. But you can compare essentially compartment to compartment or condition to condition, however you want to set it up. I apologize, guys. I must have pulled the wrong the wrong slide deck here. So these guys are all mini, but this set of figures that I have here, poor as they are, again, I sincerely apologize for this. But what I was attempting to show you here is that you could just set up a series of t-SNE plots comparing each condition across the other, and all you're going to see is that there is depletion in some locations and enhancement in others. And to me, this is not a very, it's not a very good slide because it's not prepped. But it is a means of making some sort of immediate inference as to what's going on in the data file. Okay, but again, the real way I think to make comparisons between your conditions ultimately goes back to the cluster explorer. Pardon me. And the reason that I mention this again is because of the heat map table. You can modify the heat map table to include your experimental conditions. So in this case here, I've kind of blown it up, but I've added the non-stimulated condition and the stimulated condition. And what you can see in the heat map is that the clusters that associate with the non-stimulated condition, kind of highlighted in yellow here, are the first three clusters, right? Population 0 through population 2. And then the clusters that are associated with the stimulated condition, on the other hand, are going to be 3, 4, and then everything from 6 on down. The power of this tool is that it allows you to quickly identify which populations are going to be of interest to you. So again, whatever your experimental conditions are, and you want to identify which phenotypes are driving your phenotype that you observe, or which phenotypes are present in the condition of interest, more so, let's say, than another, this particular tool will allow you to see that right away. And this, to me, is what is the enormous time saver. But again, unless you annotate the data, this is not going to be useful to you in the end, because you can't modify the table without those designations. And the other thing that you can do in this platform is you can kind of compare clustering algorithms to one another. So in this case here, I'm comparing a phenograph clustering versus FlowSum clustering. And what this tool attempts to do is match up the cluster numbers here. So cluster number 1 from phenograph and FlowSum apparently are very similar to one another, but then it gets more and more divergent as you go down in clustering, and you can set this up so that you use different metrics to evaluate how well those clusters match between the different clustering algorithms that you end up running. Okay, there are some other tools. The violin box plot is a useful one for not only getting your little violin box plots, but I also like this for the purpose of getting correlation plots. So a lot of times in multidimensional data, what we want to know is which cytokines are positively associated with which cell surface markers, and or maybe which cytokines are positively associated with one another in a given subset. And so I find that the correlation plots, which are part of this package, I find them to be quite useful for comparative analysis. Okay. Now the last thing there's two more subsets or two more bubbles or balloons to cover here. We're getting towards the end of our workflow. But the last one, and I'll mention here in terms of the comparisons and things of that nature and falling into the sort of clustering category, is we're working on putting this plugin together for the algorithm known as TrackSum. Now, TrackSum was published about a year ago out of from a group over at Centenary. And it's a very powerful tool, I think, because this particular tool allows you to watch the evolution of your populations over time. So it's similar, if you've ever done work with the algorithm called Monocle, it's similar in that sense, in that you can watch how the cells move and begin to express antigen as they move from time point 1 to time point 2, or when over disease state, or whatever the categories happen to be in your experimental setup. But this is what some of the plots or the outputs look like. We don't have the plugin available just yet, so we're still working on it, but this is something that we plan to put in to FlowJo here in the near future. I'm not exactly sure when it's going to be released, but hopefully very soon. But in this first plot here, what ends up happening is on the y-axis, you will see all of the various clusters that the TrackSum algorithm generates. And so it basically clusters all of the data that you have. So you take all your time points that you have, or all the disease states that you have, you take all those files and you import it into the tool. The tool will cluster all of the data, and then it'll monitor it. Basically takes this world clustering map, if you will, and then applies it to each individual time frame and sees how the cells move from one location to the next. And so what you have on the y-axis here is all the different clusters, and then the x-axis in this case is going to be the time points. So you have a pre-infection day, and then here there's mice that have been infected with West Nile virus for 7 days. And you can see how some of the different populations split and merge, or begin to express various cytokines over time. So in the first plot here, all of the populations or the clusters are identified by the colors that are associated with them. So for example, here, you can see the B cell clusters, which are indicated by the kind of blue, the dark blue outline, or blue fill, I should say. You can see that in the beginning, okay, you've got, looks like 3 different B cell populations. After the first day of infection, you can see that first cluster sort of splits into 2. Further down the line, on day 6 here, you can see that the original B cell cluster that you had along this line here again splits into 2, presumably because of the increased severity of the disease. Similarly, with the monocytic populations, kind of in green here, you can kind of see how those populations split very rapidly at the very beginning of disease onset, because again, they're the innate immune cells, so these guys are going to react a bit faster than, say, the humoral system would. And then in this case here, we're looking at T and NK cells. They begin to split, but of course they split a bit later on down the line. Okay, and there are other cells that are present but don't do anything. So you can see here that in this case, the plasmacytoid dendritic cells are not splitting off and becoming different clusters. They're pretty much remaining the same. The size of these little icons also kind of indicates the relative numbers of cells that are present in those populations over time. And so you can change this plot so that you can, instead of looking at the coloring being done by the population, you can actually set it up so that you can look at expression of a given marker. So your clusters are still going to be labeled off on the left-hand side. Your time course is going to be listed on the x-axis here. But as you move across, what will happen is the colors of these clusters is going to change as the expression increases, in this case of the SCA1 marker. So as you become more orange or yellow, there's higher expression of that marker. And when you're on the kind of the darker blue side, there's less expression of the marker. So you can modify these outputs, which I think, again, is going to be quite useful. There are some other outputs that the algorithm makes. So in addition to those heat map line plots, it will also create network plots. And these essentially look like minimum spanning trees that are essentially just projected into two-dimensional space. But in this case, each minimum spanning tree that is not connected is virtually a different cluster or a different population of cells. And so you can kind of see how all the different lineages of cells, how do they fare? What are they doing across the entire course of the experiment? So in this particular plot here, the colors correspond to the different time points, and the different nodes essentially are going to be the different nodes should be the different time points over the course of the experiment. So I think this legend here is actually corresponding to, oh no, these are different, I'm sorry, these are the different cell types. So we have the macrophages here that are CD11b positive. These are Lys6 macrophages, right? And then you're looking at expression of CD45 and CD80. Another way to, I guess, another possible way to project this is probably a little bit more intuitive, is the MSTs that you have on the left-hand side here. Again, here we're heat mapping by time point, so you can kind of see how things are moving. Each string, again, here is a different population of cells, and then you can color them either by population or by antigen expression. So the idea is, if you know what each string happens to be, you can figure out, kind of monitor its trajectory along that time course. So I think this is a pretty cool tool. For us in our toolbox, we haven't had a tracking tool that kind of monitors how those clusters are changing from one time to the next, and I think it'll make quite a nice new tool for you all to use in the very near future. And the last one we'll talk about here is, again, how to get back from all of these algorithmically derived populations. So imagine, again, like in the tracksum, assay here, let's say you find a population of cells or a time point that was really, interesting. You want to isolate that particular cluster, and then you want to sort them, right? You want to figure out what the function of those cells happens to be. How do you go from an output in tracksum or in any of the other clustering algorithms? How do you go from there to a series of two-dimensional gates? And the way we do that is by employing this tool called the Hyperfinder. It has a fairly simple interface that allows you to change the number of vertices that the algorithm uses to create these two-dimensional gates. It also can, you can limit the number of gates that you have. So again, if you have only a four-way sort, you can only set up 4 gates. Go ahead and do it. You can also limit it by the number of colors that you want to give the algorithm to identify it. But you basically tell it what cluster you're after. You set the algorithm towards either higher purity or higher yield. And then you just click run, and it'll go ahead and generate a series of two-dimensional gates that it kind of goes through an iterative process to refine. And then in the end, it will give you a series of gates that you can then use. You will see them in the FlowJo interface here as a series of gates labeled hi-fi. And then you could put this in the layout editor if you want to see what the progression looks like. And of course, you can export these gates to an existing Diva template or Diva experiment. So if you have a Diva experiment set up, you can go ahead and take those hyperfinder gates, export them to that experiment, and that will modify that experiment. And so then you can go on and try to isolate those cells. Okay, so with that, these are just some of the references for the different algorithms and things that I covered today. And I'll take any questions that you guys have. All right, so I see that there are a couple of questions in the Q&A box. You guys can also use the chat box if you're interested to ask questions. I'd be happy to answer any questions that you have. And I'll just kind of go through them one by one here. If not, have a lovely afternoon and great weekend. Hope to speak to you soon. All right, so there's a question about how can I delete a keyword? That is a great question, because once you put in a keyword, the only thing you can really do there is you can only overwrite it with something else. It's not easy once you add the keyword to delete it. So I can show you a little bit later in FlowJo proper how to get rid of it, but I will definitely cover that. Okay, so let's see. Is there a minimal cell events to start with? And if I'm analyzing specific immune cells such as NK cells in different donors conditions, should these cells be normalized and be equal before concatenation? That's a great question. So minimum numbers of cells, yes. In order for any of the dimension reduction tools to really work, you probably don't want to feed it less than 300 cells total, which for flow cytometry purposes, we normally don't have that difficulty. But I would be a little bit more generous and err on the more conservative side there and say, don't have less than 1,000 cells total that you feed into these algorithms. Now, in terms of if you're analyzing specific immune cells, such as NK cells with different donors and different conditions, should they be normalized and be equal before concatenation? They only have to be normalized and equal if you're interested in making direct frequency comparisons between the two. If you're interested in understanding what are the phenotypic differences, maybe somebody has multiple allelic expression of a given marker, on those NK cells. Let's say they, patient number one has, let's say, I don't know, 3 populations of, I'm just making this up, but let's say 3 populations of CD42, whereas patient number 2 has only 2 populations with CD42. In that case, you're interested in the phenotypic differences and probably not the the frequency differences between the two. But if you are interested in doing some sort of quantitative comparison and you want to say, well, the frequency of patient number 1 and frequency of patient number 2 with respect to NK cells is different, and therefore, driving the condition, then you want to make sure that you have the same numbers of cells. So in that case, Mustafa, what you can do is you can downsample to the most limiting patient. So if you have one patient that has, let's say, I don't know, 5,000 NK cells and everybody else has more than 5,000, you can downsample that NK cell compartment down to 5,000 for all the other patients. And then when you concatenate the files, you either concatenate at the NK cell level or lower. And that way you will have started with the same numbers of NK cells across the board. Okay, and that way you can make direct comparisons in terms of frequencies. Where can we find the recorded webinars? let me exit out of this and go into FlowJo proper, and then that way it'll help. So kind of weird using the pointer here. I actually have to escape out of the slideshow here. And show, there we go. Okay, so let me get back to the Q&A here. Where can we find recorded webinars? Okay, so recorded webinars, if you go to flowjo.com, so if I just click on this, this is going to take you to flowjo.com, and then you'll see this Learn tab in the upper sort of right. You go to Webinars, and then underneath the Webinars page, at kind of the bottom here, not very well highlighted, you'll see this Recorded Webinars button, right? You click on this, and then what this is going to have is a list of all our recorded webinars. So yeah, I thought I gave the normalization talk last month. So in any case, there's the normalization one. There's a compensation webinar here that was done in March. If you want to do the high dimension workflow kind of in FlowJo itself, that's here. And high dimensional tools, this is another one, you know, that's going to walk you through the actual clicks in FlowJo proper. So that's where you find recorded webinars. Let's see, next question. As you said, you preferred to not use the heat map in Cluster Explorer for phenotyping. What would you recommend for phenotyping? I like to use the line trace myself. So, you know, because I like to go kind of phenotype by phenotype, right? I'll say, okay, I'm going to look at my T cells first. So I gate on the, you know, CD3 positives first, and then I see, you know, okay, maybe I'm going to go down the helper route. So I'll click on another gate onto the CD4s, and then I'll look to whether or not I'm, you know, interested in the naives or the central memories or whatever the case may be. So I kind of approach it that way, rather than looking at the heat map, because the heat map is just, I don't know, it's information overload for me. So hopefully that it helps to answer your question, but they're all within the Cluster Explorer. So I prefer the line trace and filtering down versus looking at the phenotyping, the table itself. Can you explain again when I should use annotation and titration? Okay, so yeah, the annotation, you should always be doing that. But annotation, you want to begin this before you actually concatenate your files. Okay, so let me pull up a workspace here. Maybe I have one that's fairly recent. Unfortunately, I'm not that lucky, but I'll set one up here for you. And you can see where I would add, like where I would start to add my keywords and stuff. So let's go to documents, and I think I have my, where do I hide my DCTLR data? Sorry, guys. So these guys I use a lot of time to give a sort of an advanced webinar. And actually, let me use the template because it's already got the gates in place. And then I'll quickly show you how to put in the annotation, and then we can get back to that keyword about how do you delete a keyword. Okay, so I've got a situation like this. I've got no stem, TLR stem, and I want to annotate the data, right? So the way I do this, sort of as a one-off type of a way, is I'm just going to right-click and say add keyword here. And then I'm going to call it, usually I'm going to give the keyword some sort of designation that tells me whether or not, you know, what type of experimental condition is present. So for example, here I want to annotate the stimulation condition. So maybe I'll just call it stim condition, right, as my first keyword. I add that there. There's another annotation that I can add here as well. I have 4 files, and the files are coming from 2 different patients, right? So I probably want to incorporate the patient ID, or what I like to call the patient number, right? Put that in place. Now it's important, and I didn't mention this during the, during the PowerPoint slide, but it's important to use numbers here. Don't use text, because again, these are going to be converted into parameters that you can gate on downstream. So the first sample here, let me quickly collapse this. The first sample here, the stim condition, we're going to say it's non-stimulated. I'm just going to assign the keyword value of 1 to that. So anything that inherits the value 1, these are non-stimulated. I'm going to assign the value 2 to the samples that are toll-like receptor stimulated, right? And then if I had TNF or IL-1 or LPS, whatever the case, I would add 3, 4, 5, so on and so forth, right? Now for the patient number, the first patient here is PID1, right? Patient 1, we'll just call that patient number 1. Second patient, right? Or second sample, I should say, is from patient number 2, okay? The third sample comes from patient number 1. So I enter the value 1. Second, or fourth sample here, I'm sorry, comes from patient number 2. So I go ahead and add that, right? So this is the annotation or series of annotations that I would add to the data before I get to the concatenation step, okay? And now you probably would pick, a population after the data have been cleaned up. So in my case, I might choose the DR population here. We're just going to say select equivalent nodes, which is going to go ahead and highlight all the DR positives. And then I like to right click here and say export concatenate, because it's in the same vein here. Okay, so once you've done your annotation addition and you're ready to concatenate, you choose the populations you want to concatenate or merge together. If you want to downsample, again, back to the question about whether I should have the same numbers of cells, if you want to do, frequencies that are the same, or you want to make direct comparisons between frequencies that appear in different patients, then you can downsample here to a specified number of cells. And in this case, I would just make it whatever the most limiting sample is. I'm going to do a very easy number here of 10,000. Okay, I want to make sure this is on concatenate, and here is where you're going to put in your keywords. Okay, so you say choose under the additional parameters box, and then you go ahead and you scroll down, find your patient number keyword, hold down the control key, find your stim condition keyword, highlight them both or as many as you have, and then click OK. That's going to add them to it. And then we can, I don't know, call this webinar or something like that. And then you can go ahead and concatenate the file. If you want, you can dump it into the existing workspace. Okay. And now when I have the concatenated file, it's going to have 2 parameters, the patient number and the stim condition, right? There's patient, and this condition, stim condition 1, right? This is the non-stimulated. These are stimulated. And if you doubt me, you can always just kind of, look at the expression of some sort of, marker. In this case, you can clearly see the TNF, right, is being expressed in this population, but not this guy. Okay. Patient number, same thing, patient number 1, patient number 2. And all you have to do here is gate on it, right? You can either create a gate on the, this way if you want. This is patient 1. Right? Create a gate over here, and this is patient number, number 2, PT2. Now, if you want to do it the super fast way, let's go to stim condition. I like to do this. I linearize the axis, and then I tell this to histogram itself. And the fast way is to right click and say create gates on peaks. It'll auto gate these guys for you. Sometimes you have to stretch out those gates, right? But then you get them, and you just check your workspace here to make sure that the gates are proper. I'm missing 1 cell in patient number 2. No big deal, but I can stretch out the gate. But there's patient 1, patient 2, stim condition, 0 versus 1. You can do any kind of cross comparison that you want, right? If we want to recapitulate all 4 files, right, that we had, there we are. Patient number 1's non-stimulated, patient number 1's stimulated, right? Patient 2 non-stim, patient 2 stimulated. Okay, so hopefully that answers those questions. So let me move on to the next one. If there are samples with different range of data quality, whether we are allowed to compare these samples together after normalization and data quantification. Well, the judgment call is going to, really be up to you, Nafisa, because the sample quality, the problem there is that if you have one poor sample in the batch, it's going to skew your t-SNE, it's going to skew your clustering results. And what is going to end up happening is you're going to have to go back and find, all these novel populations, or the strange looking populations. What you're going to find is that that's going to most likely come from the poor sample that you had in the data set. So what I would do when I'm kind of reviewing data files to go into the concatenation, I would look at their compensation, and I would look at the data quality. Is it overcomped? Is it undercomped in a particular location? I suppose if all the files are undercompensated or overcompensated in the same area, you're probably safe, right? Because you could say, okay, well, it's not just one file, it's all of the files that have this problem with compensation. So if they all are showing the same error in the same location, then you're going to have to do less work working backwards to figure that out. Okay, but if you have only one, what do they say? That's it takes only one bad apple to spoil the barrel. So that's kind of true when it comes to the use of these tools and a single sample that is problematic. So I would try to chuck the low quality samples, or at least group the low quality samples together and maybe compare them to one another rather than mixing them with the high quality stuff. Okay, the next question. The normalization seminar skimmed over the necessary controls. What type of controls are required for cytonorm? We're using a tumor that express varied amount of antigen. So finding a control that consistently expresses all the markers has been difficult. Okay. Yeah, that's a great question, Jonathan. And I apologize for skimming over the controls that are necessary, but what you need are, for every condition, right? So again, looking at your tumor that expresses varied amount of antigen, what you're going to want to do is go antigen by antigen, right? So characterize the tumor that you have as best as possible. And then what you want to do is you want to have a control that has, let's say, if there's no stimulation condition or sort of any kind of agonist that's being applied to the sample, you basically need you're basically going to need tumors that were collected on day one and a replicate of that, and then tumors that, let's say, are collected on day 7 and a replicate of that. So for each condition where you expect that antigen expression may change, you need to have a control, right? But it's essentially a reference control. So it's not a true testing control. It can just be a split piece of the sample that comes on day 7, right? It's just that you're saying, okay, this half of the tumor I'm going to incorporate and use as the sort of reference control, and then I'm going to treat the other half of the tumor as the quote unquote sample. The point is that the algorithm just needs to know, okay, when I'm looking at what you are saying is a control, it has, let's say 5 peaks across 2 different channels. So that control has to have those 5 peaks, and then hopefully the test sample has only 5 peaks or less. Right? If you expect that you're going to have 7 peaks across 2 channels, then you need to have a portion of a sample that has those 7 peaks represented. Does that make sense? Okay, I'll let you get back to that one. So that's the Q&A box, and I see that we have some stuff in the chat box here. Okay, so There's a question about plugins. My plugins don't work. I receive an error each time I use them. Flow AI has failed to produce the expected derived parameter. Okay, so for the problems with the plugins, what I would highly recommend is to simply send an email to FlowJo@bd.com. And what will happen is just explain, just copy and paste what you've written me here. And what will happen is they will set up a screen share session with you and, figure out what's going on with your computer, and they'll get it to work. So just again, the email is just FlowJo. So that's spelled FLOWJO, right? Just like the tab shows here, @bd.com. Just paste your comment that you have here, Alan, in your email, and they'll get back to you fairly quickly, and then they'll just set up a time to help you with it. Kauthar, we don't know exactly when Traxum will be available. So far, I haven't gotten even a test plugin in my hands yet. So I'm hoping that it's going to be done by the end of the summer, maybe sooner. But we will definitely have a webinar when it becomes available. We'll show you how to use it, etc. So that's coming. I wish I had a better answer for you. When to use compensated or uncompensated when concatenating populations? Great question. Okay, so when to use compensated or uncompensated when concatenating. Now, you guys saw me here. I concatenated these guys together, and I had chosen the option, right, to concatenate uncompensated parameters. So let's do select equivalent nodes again. Let me get you to this menu so that we're all on the same page here, and so we can reference what the question is asking. Okay, so in the concatenation menu here, you have the option here to concatenate all uncomped or concatenate all compensated. Now, I would tell you guys 99% of the time, this is the option you want, all compensated. So you want to choose this when you have samples that come from different days and have, the different compensation matrix associated with it, right? So you have samples that you got on Monday, and Monday's samples will have Monday's compensation matrix. Friday's samples are going to have Friday's compensation matrix. So even though the panel may be the same, the compensation matrix values are going to be different from Friday to Monday, and they should be. I mean, the instruments drift, the organic dyes are always experiencing redox, so their values are going to be different. So you want to preserve each compensation matrix on all of the individual files that you have. You want to use this function that says all compensated parameters. Okay, now if your samples happen to come all on the same day and they all get the same compensation matrix, you could get away with this option here, which is all uncompensated, because what ends up happening, as you saw, once you get back into the workspace, that file will automatically pick up the compensation matrix that you were working with. Granted, if you put it in the workspace that you're currently working with. Okay, so when I dumped it into this workspace, it automatically picks up the compensation matrix that's associated with these files. And here you can see there's only one compensation matrix in the entirety of the workspace, right? If I come over here, you can see that if I double click on this guy, there's only one compensation matrix. Okay, so if again, I had multiple comp matrices, or I had samples that come from different days, I'm going to make sure that I want to do all compensated. Okay, and that'll be 90% of the time. So hopefully that answers that question. All right, and then last, we'll talk about the deleting of a keyword. So let's go back to this workspace real quick, and you can kind of see here that I have stem condition. I suppose I can go through and delete them one by one, but that's a little bit onerous, right? If I go through here and I click delete on all of them, that's how you could delete it, but you can't get rid of the column header here. So you would have to start a new workspace if you want to use the same column header, or you just create a new keyword and call it stem condition 1 or something like that, just making it different than the current one that's present. Okay, sorry that one took so long. All right, so Jonathan asks, do the controls need to be exactly the same for each run? We've seen freeze thaw process lose expression in some markers. So again, there, in the samples that you're seeing the freeze thaw loss, you would basically have to split that tube that gets the freeze thaw and treat it as a different control, right? So you're going to say, okay, the samples that come from this freeze thaw tube, half of that sample I'm going to consider a replicate or a sample, test sample. The other half I'm going to use as a quote unquote control, because it's going to represent the antigen expression for that particular tube for that particular time point. So it's rather tedious with respect to the controls that it has to have, but that's essentially what you would have to put forward. All right, are there any other questions? Clearing out the Q&A box here, and I think we've answered all of them in the chat box. Okay, so again, if there's no questions, by all means, have a great rest of your day. Enjoy the weekend. And if you have any questions for me, my email is jack.flowjo@bd.com. And I see that there is a hand raised. Go ahead and type your question in the chat box or in the Q&A box so that I can see what it is that you want to ask. Okay, otherwise, I'll bid the rest of you a good afternoon. So Javad, you're raising your hand, but I do not see a question. Let's see here. You're welcome, Sid. All right. So many places on Zoom here to type a question. So it gets, I have to check through a lot of different menus here. All right. Well, thank you all and take care.